Now let's talk about the third part of the chapter, that is about the conductivity. So in the conductivity part of the chapter, that means let's talk about the first metallic and electrolytic conductance. Now the conductance means it is the ease of the flow of electron through any substance. The substances which conduct electricity generally they are either metallic or we consider it as a electrolytic. Metallic conductance are those conductance generally they conduct electricity in solid state as well as in liquid state, but electrolytic conductance are those which conduct electricity only in molten state or in aqueous state. So here I am talking about the conductivity. The conductivity, so as I said, there are the two substances. We had classified the substances as a metallic or electrolytic. So let's see the difference between the metallic conductance and electrolytic conductance. Metallic conductance. From the lower standard only we are studying that for conducting a electricity or for conducting a heat, the requirement is the free charges. That the free charges are required for conducting electricity. So in case of metallic conductance, the charges which conduct electricity is nothing but the electrons. So here the electricity is conducted by the flow of or by the free movement of electron, I can say. So here the electricity is the electron is responsible for conducting electricity, while in this case there is no free electron for conducting electricity. But in case of this electrolytic conductor, I can say that here the electricity is conducted by the free ions. There are the free ions, that is a positive and negative ions, or I can say cations and anions, which conduct electricity in the case of electrolytic conductance. Then in the second part, that is the second point, in case of metallic conductance, when the electricity is flow, when there is a flow of electricity, there is no movement of matter. Matter do not move. For example, suppose if I am passing electricity from the copper wire, this is the copper wire which contains the copper ions. So when the electricity passes through it, that copper ions never move from here and there. There is only free electrons movement. But in case of electrolytic conductor, when the electricity is passed, there is a movement of matter. Movement of matter, for example, suppose I can say that if I am passing electricity from the molten NaCl, there is an anode and cathode. Anode and this is cathode. It's a molten NaCl, that means the NaCl is in liquid state. So there is a two ions, that is Na plus and Cl minus ion, and matter means once I use a matter, that means NaCl, or I can say positive one, Na plus and Cl minus ion. When we pass electricity, then on passing electricity, these ions also start migrating. Na plus migrates to this and Cl minus migrate to this. So Na plus, after moving to the cathode, it gains electron and forms sodium metal, while the Cl minus ion, after moving to the anode, it loses electron and produces Cl, that is Cl2. So chlorine gas is formed. Then third, I can say, since there is no movement of matter, no movement of matter, there is only free movement of electron. So I can say that here the no chemical reactions takes place. No chemical reactions takes place. While in this case, you can see that here I had written the reaction initially before passing the electricity. There was Na plus and Cl minus ion inside the solution, or inside the means in an electrolyte, but after passing electricity, there is no Na plus and Cl minus. Instead, we are getting a metal and a gas. That means a reaction has occurred, due to which Na plus get converted into a sodium metal and the Cl minus ion get converted into a chlorine gas. So there is a chemical reaction takes place. In the case of this, if I am increasing a temperature, on increasing a temperature in case of metallic conductance, the conductivity goes on decreases, conductivity decreases. That means I can say that the conductivity is inversely proportional to the temperature in the case of metallic conductor. While in the case of this electrolytic conductor, as it increases the temperature, on increasing the temperature, the conductivity also goes on increasing. That means here it is directly proportional. Now the question arises that why the temperature is directly proportional in this case and here it is inversely proportional. Then simple answer, on increasing a temperature here the more and more dissociation takes place. Due to that more and more dissociation, more number of ions are produced, and if the more number of ions are there, then the conductivity is going to be higher and higher. But in the case of metallic conductor, where the electrons are responsible for the movement for carrying electricity, and here the conductivity, whether it will conduct electricity with a very high speed or low, it totally decided by the flow of electron, the direction of the flow of electron. At low temperature, all the electron moves in the same direction. But when the temperature is increased, there is a excitation. The electron gain that energy on increasing a temperature. They excite to a higher energy state, and after exciting, they again return to the same energy level. And when they return to the same energy level, they create or produces randomness in a direction. That means due to this excitation and again coming back to the same energy level, causes the randomness in a metal, that is a randomness during the movement of the electron, and due to this randomness I can say that here the conductivity goes on decreasing on increasing a temperature. So in case of metallic conductor can conduct electricity even in a solid state. Example of the metallic conductor, I can say simply that all the metals are the example of metallic conductor which conduct electricity even at a room temperature, even in a solid state. But in case of electrolytic conductor, they conduct electricity only when they are in a liquid state, or I can say either they are in a molten state or in an aqueous state. That means either you heat it, convert it into liquid, or by dissolving it into water, it can be converted into liquid. Okay, so when we are talking about the conductivity, as I said, we have metallic and this. Here, since there is no chemical reaction is taking place, so throughout the chapter, we are not learning anything about the metallic conductor because we are talking about the electrochemistry, that means which deals with the chemistry part also, and for the chemistry there should be a reaction. So since no reaction is taking place, so we are not doing anything about the metallic. Throughout the chapter we are doing only and only about the electrolytic conductor, where some chemical reaction also takes place when electricity is passed. Now when I am talking about the electrolytic conductor depending on its conductivity, the electrolytic conductor has been divided into two parts. The first one is called as a strong electrolyte, and the second is called weak electrolyte. The strong electrolyte is the one which dissociates completely. And hence produces more and more number of ions, and dissociate completely, therefore I can say that degree of dissociation is approximately equal to 1, or I can say 1. And weak electrolyte which dissociate partially. Dissociate partially means only a few fraction of the molecules get dissociated into ions, and while the other molecule remains undissociated. And since dissociate partially, the less number of molecules are dissociating, therefore the alpha value is less than 1. So example for strong electrolyte, I can say that approximately all ionic salts are the example of this, all ionic salts. All strong acids are considered as the strong electrolyte. All strong bases are considered as strong electrolyte because they all dissociate completely. Ionic salt, like I can say NaCl, KCl, ammonium chloride, ammonium nitrate, calcium chloride, calcium fluoride, etc. Strong acids, like I can say HCl, HNO3, HI, HBr. Strong bases, sodium hydroxide, potassium hydroxide. While in this case, the weak electrolytes are generally weak acids. weak acids which dissociate partially, and the weak bases which again dissociate partially. The weak acids, like I can say acetic acid, HCN, H2CO3, oxalic acid. Weak bases, example I can say that ammonium hydroxide, copper hydroxide, FeOH3, etc. So here we have, overall we have two different types of electrolyte, the one which can dissociate completely and the one which dissociate partially. Since it dissociate completely, so produces more number of ions, and hence here the conductivity is very high, while in the case of this, since it produces a less number of ions, therefore the conductivity is very low. The next we have the electrolytic conduction. Electrolytic conduction means here now we are going to learn about the different terms which are related to the conductivity of the solution or the electrolyte. As I said, here we are in the chapter, we are learning only about the electrolytic conductor, not about the metallic, because in case of metallic conductor no chemical reaction takes place. So we have learned about the Ohm's law, according to which the current flowing through a conductor is directly proportional to the potential difference across the conductor. So we can write that here I is equal to V into R, where R is a constant, or I can say that R stands for the resistance. So here the R stands for resistance. Now let's talk about the resistance. Resistance. The resistance which measures the obstacles to or obstruction to the flow of current. Means I can say that if a metal which or a substance which conduct electricity without any resistance is called as a superconductor. So here there is a, when we measure the conductivity of anything at a given temperature, then there is a certain obstacles which resist the change, or which oppose the flow of the current, and that obstacles is measured in terms of resistance. And here we have relation that resistance is directly proportional to the length of conductor and inversely proportional to cross sectional area. So R is directly proportional to L and inversely proportional to A. Therefore I can say that R is equal to rho into L upon A, where rho is called as resistivity. Or specific resistance. So here the rho is called resistivity or specific resistance. Now let's talk about the unit of the R and rho. R, the unit for R, it is ohm. Now rho, that is a resistivity or specific resistance. So here we will have a formula for the resistivity, that is resistivity is equal to R into A upon L. So if cross sectional area is equal to 1 meter square, and L is equal to 1 meter, then I can say that here the resistivity will become equal to R. So resistivity is defined as the resistance of a conductor which is 1 meter in length and 1 meter square in a cross sectional area. That is, a conductor whose length is 1 meter and the cross sectional area is a 1 meter square, and when resistance is measured across such conductor, then whatever the resistance value we get is called as resistivity. Now from this resistivity formula is, actual formula is R into A upon L. So if I wanted to know the unit for the resistivity, so the unit of resistivity is R, it is ohm, area is meter square upon length is meter. So it is nothing, so the unit is nothing but ohms meter. Or I can say it is ohm centimeter. If the length is measured in centimeter, then in ohm centimeter is the unit for the resistivity. Then after the resistance and the resistivity, next we have conductance. And conductivity. Conductance, it is represented by capital letter G. The resistance measures the obstacles to the flow of the current, while the conductance measure the ease for the flow of current. Means with means it is, or I can say it measure the ease to the flow of the current. That means I can say it is nothing but reciprocal law of resistance. So G is equal to 1 upon R. Since G is equal to 1 upon R, so unit of G I can say that 1 upon R, resistance unit is ohm, so it is going to be per ohm, or when it is a per ohm, then it is ohm. Per ohm is also known as Siemens. It is represented by the capital letter S. So it is unit of G is per ohm or Siemens. Now, since the G is a reciprocal of R, therefore I can say that R is directly proportional to length of conductor and inversely proportional to the cross-sectional area. Therefore, I can say that G is directly proportional to cross-sectional area, that is a reverse or reciprocal, and inversely proportional to the length of conductor. So for removing that proportionality sign, I am just introducing a constant A upon L. This constant is, in a Greek word, this constant is known as kappa, K-A-P-P-A. So G is equal to G is equal to kappa into A upon L. So here this, if again here A is equal to 1 meter square and L is equal to 1 meter, then I can say that G is equal to this, where this term is called as conductivity or specific conductance. So this kappa is called as a conductivity or specific conductance. So G is equal to kappa. So K or kappa is defined as the conductance of a conductor. It is nothing but the conductance, the definition for this, it's nothing but the conductance of a conductor, which is again a 1 meter in length and 1 meter square in a cross-sectional area. Now for the formula for this, K, that is equal to G into L upon A. So unit of kappa, that is conductance, is per ohm. This length is meter square, meter upon meter square, that is per meter, or I can say it is per ohm. Instead of meter I can write per centimeter also, or we can measure per ohm, instead of per ohm I can write Siemens, and Siemens per centimeter. Now if you will see the formula for the rho and kappa, then you will come to know that they are exactly reciprocal of each other. This can be written as, here I can write it as a 1 upon G, instead of R I can write 1 upon G into A upon L. So 1 upon G upon L, that means this rho and kappa, they are inversely proportional to each, they are reciprocal of each other. Next we have molar conductivity. Molar conductivity, just to understand this, let us consider this. We have two solutions. The first solution, both the solutions are containing NaCl, that means they are the aqueous solution of NaCl. But this contains 0.5 moles of NaCl, and let the solution is 1 liter. And here 1 liter solution again, but the solution contains 1 mole of NaCl. So we have two solutions, and both solutions are made up of the same electrolyte, that is NaCl. Both the solutions are same, but the difference is that here the first one is containing the 0.5 moles of NaCl and the second one is containing 1 mole of NaCl. 0.5 moles of NaCl in 1 liter means I can say it is a 0.5 molar solution, while this can be considered as a 1 molar NaCl solution. When NaCl is dissolved in water, ultimately it will produce the ions like Na plus and Cl minus ion inside the solution. Okay, now since it will produce ions, so on keeping an electrode they will conduct electricity. So I just measure the conductivity of both the solutions. When the conductivity of this solution is measured, suppose I got the conductivity of this solution as a 12 per ohm per centimeter, while when the conductivity of this second solution is measured, I come to know the value is 18 per ohm per centimeter. So we got a conductivity for both the solutions. When I'm talking about that second one which contained 1 mole of NaCl, it's a conductivity, instead of K here I can write lambda also. This is capital lambda, so lambda can also be written, which is which is also known as a molar conductivity. But can I use a word lambda for this conductivity? Then answer is no. Here we cannot use lambda term for this solution. Here it is only called conductivity. Well, for this I can use a word conductivity as well as molar conductivity. So what is molar conductivity? Why we cannot use a molar conductivity term in this case? Then simply I can say that molar conductivity is the conductivity of only those solutions which contains 1 mole of electrolyte. Means it is a conductivity of a ions which is produced by the 1 mole of electrolyte. So here I have taken 1 mole of electrolyte, that is 6.022 into 10 raised to 23 molecules of NaCl which will produce ions. So the ions, if the ions produced by 1 mole of electrolyte conduct electricity, then we use a term molar conductivity. If the electrolyte is less than or more than 1 mole, then then we just use the term conductivity. So it's a conductivity and molar conductivity. This is the difference, that molar conductivity is the conductivity of 1 mole of conductivity of a solution containing 1 mole of electrolyte. After this, we have the relationship between the molar conductivity and conductivity, that is lambda and K. The relation is the lambda is equal to K upon C, or I can say it's 1000 K upon C, where K, or I can use a term kappa for this, that is conductivity, where K is this is conductivity, or I can use the term specific conductance. C is a molar concentration. Molar concentration, whose unit is generally moles per dm cube, but after multiplying by 1000 it becomes moles per centimeter cube. Means here the C is actually in a dm cube, but when I multiplied moles per dm cube, but when I multiply then it becomes moles per centimeter cube. So currently it is in moles per centimeter cube after multiplication. Now let's see the unit for lambda. The unit for lambda will be 1000 K. K unit is per ohm per centimeter, while for concentration it is moles per dm cube, but as I said, after multiplying by 1000 it becomes moles per centimeter cube. So now it is moles per centimeter cube. Therefore I can write moles per ohm. This centimeter cube will become per centimeter cube will become centimeter cube. So it is per ohm per mole. Centimeter raised to -1 and +3 will become per centimeter square. So it is per ohm centimeter square per mole. Or instead of per ohm we can use the term Siemens also. So Siemens centimeter square per mole. So this is the unit of a lambda, that is per ohm centimeter square per mole. After this, the relationship between lambda and concentration of solution, or I can use the term dilution of a solution. So here we have a relation that lambda is equal to K upon C, or 1000 K upon C. So simply from the formula you can say that lambda is inversely proportional to concentration. It means as the concentration increases, the lambda value goes on decreasing. And at the same time for K we will have a formula that K is equal to lambda C upon 1000. That is, K is directly proportional to concentration. That is, as the concentration increases, the conductivity goes on increasing, but at the same time as the concentration increases, the molar conductivity goes on decreasing, because as the concentration increases, the number of ions goes on decreasing produced by the 1 mole of electrolyte. So lambda concentration, or I can say concentration, is inversely proportional to volume. So here we can write lambda is directly proportional to volume. That means as the dilution is carried out, the lambda value goes on increasing. Well, in this case it will be K is inversely proportional to volume. That means as the concentration decreases means we are diluting the solution. So as the dilution is carried out, the K value goes on increasing. So this is the relationship between the lambda and concentration, that is molar conductivity and concentration, and conductivity and concentration.